Okay, I guess we can start a minute. I will wait a minute. Because we can start with the logistic thing. So we will have class day after tomorrow and next Thursday, but we won't have class on next Tuesday. I'm in San Diego for Biophysical Society meeting. And I would have taught on Zoom, but I will be on a plane then, so I cannot teach. So no class next Tuesday. And I will release the second homework on Thursday after end of the class, and you will have a week to do it. And I will grade both homeworks and also release answer keys before the midterm. The midterm will be take home. It will be released a day before 2nd of March, something like that. And you will have day before? No, morning of 2nd of March, early morning 2nd of March. And you will have a wonderful weekend doing it. You can take as much time as you wish. And it will be due in class on Tuesday. Okay. So it will be open internet, open books, whatever you want to do. Just don't copy from each other. Any questions about this? Okay, let's get started. So today we are going to talk about canonical ensemble, which we started last time. And the whole idea was that when we are looking at microcanonical ensemble, it's an isolated system. It's kind of boring. It's better to think about a system where the temperature can be controlled, where you can have some energy fluctuating with the environment. So we will study how to set up such an ensemble. And the main question will be how to calculate. As I said, in statistical mechanics, the question is always to calculate the probability of microstates. What is the probability of observing a given microstate? We will introduce the notion of a canonical partition function, which is similar to the microcanonical partition function. Microcanonical partition function dependent on NVE. This one will depend on NVT. And we'll show how this connects to thermodynamics. And then we will get started with calculating averages and fluctuations out of such an ensemble. Okay, so let's get started. So no class next Tuesday, okay? So what are we trying to do? We are trying to think about a system which has number of particles n, volume v, but which can exchange energy with its environment. And this environment is often written as, well, it can be called environment, or it can be called a bath, or it can be called a reservoir. There is no difference between any of these terms. It's the same idea. Okay, so you have a system which has fixed number n, fixed volume v, and energy E, which can fluctuate, which can change because it is exchanging energy with the environment until it comes to thermal equilibrium, until there is balance. So the value of this energy can take different values. Let's say it can take the value E1. Let's say there is another possibility of this system where the number is n, volume is v, and now the energy can take E2. Again, this is also fluctuating and exchanging energy in the environment, and so on and so forth. You have a third possible copy where you have number n, volume v, and energy E3, and that also fluctuates, and you have lots and lots of them. So, and all of these are exchanging energy with the environment or the bath or the reservoir, and that we assume to be much, much bigger. That is something that looks like this. And overall, this thing is thermally insulated. Nothing can get in or out of the bath itself. It's a much bigger bath. So total, so inside we have different copies of the system. That they don't talk to each other. They're independent copies. And here we have a bath. And the system plus bath is insulated in every possible way. In other words, the system plus bath together can be treated as a microcanonical ensemble, right? Because it's isolated. There is nothing that's going on in exchange with the environment. There is no environment outside the bath, right? Bath sums up everything. So another word, we like to be grandiose in science. So the another word for it is universe. That's it. There's nothing outside it, right? System and blood, that's it. There's nothing outside it. So now here what we have done is to create independent copies of the system. This is really the same as just keeping one copy of the system and observing it over a very long time, right? That's the ergodic hypothesis. That's what we would like to do, but ergodicity allows us to do something like this. So those of you who came late, there is some information in the first page of the notes. There is no class next Tuesday. Homework will be released this Thursday, and the midterm will be take home, open internet, open everything on 2nd of March. I will talk more about the midterm when I release it. But main point for today is that we have a class on Thursday, but we don't have a class on Tuesday. So we have this system set up, and what we want to do is, let's say we have a certain copy, we call this E3, but let's call it E new, right? A certain given microstate of the system, E new. And we want to calculate what is the probability of finding the system in this microstate E new, right? We could also be interested in finding the system with n number of particles. What is the probability P of n? Any ideas? Close enough. It's a delta function, right? So it's really delta of n. It's proportional to delta of n, right? It's exactly 1 if you normalize it, but it's just peak exactly at 1. Similarly, P of volume is proportional to delta of V. P of E nu, we will show, is proportional to e to the power minus beta multiplied by E nu, where beta is our inverse temperature. 1 divided by Boltzmann constant divided by temperature. That's what we are going to show today. How does this follow? And in order to do this, yeah, go ahead.
The function of n minus some constant.
The same idea. The same idea. You're correct. I could introduce a new variable and then call the number n, blah, blah, blah. But life is short. Let's get the spirit right, okay? Huh?
Let's keep the classes.
Yeah, no, that short. You gotta have your priorities. And okay, where was I? So in order to calculate this P of E nu, we are going to make two assumptions. First assumption we are going to make is that system plus bath is insulated, right? Total there is a microcanonical ensemble. And the second assumption first assumption we are going to make is system plus bath is equal to a microcanonical ensemble, okay? And the second assumption we are going to make is that the system is much, much smaller than the bath. The number of degrees of freedom in the system is very, very few. The bath is enormous. It's like something in an ocean, right? The ocean is way bigger. There's so much going on there, and something like that. So in order to do this, how are we going to solve the problem? And we want to show that P of E nu is proportional to e to the power minus beta E nu. This is what we want to show. In order to show this, how will we proceed? So let's start. The first idea is that heat bath, or just call it bath, it's a thermal bath, which is, you could also have a number bath, right? So this is a heat bath because it is exchanging energy in and out of the system. You could also have a number bath, for example, but they're all bigger systems, so they are a bath. So bath plus system is equal to isolated. So what does it mean about the energy of the bath plus energy of the system in some microstate nu? This is going to be a constant E, right? It's an isolated system. We don't know what the value is, but it's going to be some constant. So if you decrease the value of E nu, the value of EB has to go up, and vice versa. The total is insulated because, yeah.
Since the bath is so much bigger than the system, can you not just approximate that to be EB?
Yeah, we'll do things like that. In physics is all about making approximations just at the right time. Otherwise, all Taylor series will just become f of x is equal to f of x naught, right? If you ignore the first derivative, right? So that's the spirit, but not so quickly, okay? That's exactly what we'll do. Yeah, we'll not be left with anything. So the idea being that if this microstate value has E1, then the bath is going to be E minus E1, right? If this has value E2, then the bath is going to be E minus E2, something like that, so on and so forth. And so this follows from assumption number 1, and assumption number 2 can be written as EB is much smaller than E nu, which is what Vedant was saying. That's what we are going to use, but a bit carefully. So what we are going to do now,
It's the other way around.
oh, you guys are paying attention. I'm a bit pissed today. I just got a grant rejected like 5 minutes ago. It's horrible. It's okay. Let's move on. Science is like 95% about rejection, as you are all probably learning. And the more senior you get, the rejections happen at a rate which is like mind-boggling. Anyway, so let's try to focus on the system and bath together as a NVE ensemble. Okay, that is the idea. So we will focus on system plus bath together as a NVE ensemble. No class next Tuesday, okay? And so in order to do this, we are going to do a bit of counting, okay? So let's make a table where the first column, we are going to denote the state nu of system. The second column, we are going to write down number of ways of system, number of ways the system can take, the number of microstates possible for the system. In the third column, we are going to write down number of ways of bath. And in the final column, we are going to write down number of ways of system plus bath. So Chandler does not go into this much detail, and he kind of skips the second column altogether. The reason being that the number of, and you will see why that is an okay approximation. This is what we are going to count, okay?
What do you mean by waves?
You'll see the number of microstates. Let me just call it number of microstates, number of microstates. Okay, so let's say the state nu of the system. So what do we need to denote the state of the system? Just the energy value, right? N and V are constant, right? So we can denote the state of the system if we know the energy of the system. So let's say E nu is equal to E1. Then in this case, the number, and this is where it gets a bit abstract. Now you have fixed the energy, right? So for a moment, you're treating the system as if it was a microcanonical ensemble, right? You're not allowing the energy to change. It's a thought experiment, Gedanken. So this is going to be some omega cis as a function of E minus E1, while this one is going to be omega bath. Sorry, I mixed the E. This is not E1, this is just E1. For the system, it is just omega cis as a function of E1. And the number of microstates of the bath is going to be some omega bath as a function of E minus E1. If E nu is equal to E2, this is going to be omega cis E2 omega bath E minus E2. And in this thought experiment, we have fixed the energy of the system and of the bath, right? So the total number of microstates can be multiplied because we have fixed the value. We have just taken a snapshot, but if nothing is going on, no exchange is happening, or just frozen the exchange at one point. So the total number of ways of the system and the bath is going to be a product of omega cis E1 multiplied by omega bath of E minus E1. For when E nu is equal to E2, this is going to be omega cis E2 multiplied by omega bath E minus E2. So just focus on this column. Why do we want to focus on this column? Because what we really want to do, and I don't need the table to go much longer, so I can just write it here. What we want to do now is to find the number of ways system can have energy E nu and bath can have energy E minus E nu. That number of ways, or the total number of microstates, it's coming from this third column over here, right? That's exactly what we counted down. This can be taken one step further. Why can be taken one step further? If I replace the number of ways with probability, right? So we are just switching from counting to probability. The probability of finding the system in energy E nu and the bath in energy E minus E nu is therefore proportional to this quantity in the third column, right? So, and I will just write down the statement which I wrote on this last thing. I will write down in a slightly different manner, and I will say now that probability, not number of ways or number of microstates, but the probability of finding system in microstate E nu. And I'm no longer going to write and bath in energy E minus E nu, because that is redundant, right? The full system has energy, system plus bath has energy E. So as soon as you know that the microstate has energy E nu, what is the energy of the bath? E minus E nu, right? So that's kind of redundant. So probability of finding the system in microstate E nu is going to be proportional to omega system E nu multiplied by omega bath E minus E nu. If you read Chandler, he totally ignores omega system E nu. He never even talks about it. He just talks about omega bath E minus E nu. And it will become clear in a moment why it is an okay argument. Okay, so let's call it. So we know our P nu is proportional to this thing. Let's call it equation number 1. So far, it doesn't look anything like your Boltzmann probability e to the power minus beta E nu, right? This looks terrible. Like, what are these two strange probabilities? So let's move from here and do something. In statistical mechanics, when you get confused, these are like one day when I become very famous or something, I'll write a book, 50 things to do when you're confused in statistical mechanics. And one of them would be, when you get confused, take a log of an exponential, which means nothing, right? The same thing is written over here. And all I'm saying is put a log and put an exponential. But it actually, oh, sorry. No, that's a bad rule. Don't take log of exponential, take exponential of log. And there is a profound difference, as you will see. Because log of exponential, Stirling's formula cannot help you. If you take exponential of log, you can make use of Stirling's formula, right? That's the whole idea. So this thing that I wrote above can be written just as P nu is proportional to exp of log of omega cis E nu multiplied by omega bath E minus E nu, right? Everyone happy with it? I did nothing. I just took log, exponential of log, not log of exponential, okay? And the other thing in my rule book will be integrate by parts. That's going to show up soon. So what can we do with this? This can be written further as exp of log of omega cis E nu plus log of omega bath E minus E nu. And now we can become approximate. So far it's exact. There is no approximation apart from what we stated, our assumption. But now we can actually use that the number of microstates the system can take is always going to be much smaller than the number of microstates the bath can take, right? It's like, I don't know, who should I send swimming in the ocean? Let's send Alex swimming in the ocean, right? It's Alex is swimming in the ocean, exchanging energy with the ocean. And I'm trying to describe the number of microstates Alex can take versus the number of microstates Pacific Ocean can take. There's no comparison, right? There's so many more, right? Do you agree, Alex?
At least no thermal equilibrium in this case.
We assume equilibrium. There is equilibrium is instantaneous. We are in statistical mechanics. Yeah, in the real ocean, it's anything but thermal equilibrium. A shark came and ate Alex. Game over. Sorry. I hope you lived a good life. So, so we can make this assumption, and which allows us to go one step further and write down this equation as P nu is approximately proportional to exp of log of omega bath of E minus E nu, right? We can ignore this term. This is very small, not on its own. On its own, Alex has an Avogadro number of degrees of freedom. He would like to claim, I know I have lots of degrees of freedom, but compared to the ocean, it's very few, right? So this is very small compared to this omega bath, right? So we can ignore it. So we are left with this. And this is what I meant, the magic of e to the power log in statistical mechanics. Now, all of a sudden, you again have e to the power log, but now it's much simpler. But we will keep working with this log for a reason, okay? We will write this down as equation 2, and let's focus on this quantity over here. So we have, any questions about this? So we have log of omega b, I will just call it bath as b, okay, omega b, E minus E nu. And we have to think about this. What can we do now? Is E nu, how does E nu compare to E? Much smaller, right? So this is where Vedant would have come and said, oh, wait, just write it as log of omega b E. Ignore the E nu. That would be a bit terrible, right? There is no E nu. We want an expression that relates to E nu, right? So this is true, approximately, right? If we really want to think about a more accurate approximation, what do we have to do to this term? Taylor series, right? We have to add a second term. So we will expand this along E, around E, okay? So with the first term in the Taylor series is log of omega b E. The second term is going to be minus E nu multiplied by partial derivative of log of omega b by partial E at constant NV, right? It looks horrible, but is it really? Have we seen partial log of omega b by partial E at constant NV before? What is it?
Just 1 over beta.
1 over what?
Beta.
It's beta, but beta what? We have to be careful.
It's a derivative of beta.
No, it is beta, but beta of what? Is it beta bath? Is it beta system? It's beta bath, but is that different from beta system? Why not? Thermal equilibrium, right? So this thing over here, if you remember microcanonical ensemble, we defined our temperature. We did not define, we said, since log omega is entropy, right? That was our connection. Only in the microcanonical ensemble. That's why we had to look at, that's why Chandler's book is a bit terse. He does all of this in like one paragraph. And it took me like 5 years to get a sense of it. So my professor definitely did not go through in this much detail. Also, I used to fall asleep in the class. It's not very good. So it was at 1 p.m. What can I do? So this thing is equal to beta bath. But that per construction is equal to beta system, right? Because there is thermal equilibrium. So we are just going to call it as beta, which is 1 over kBt, because we are talking about an NVT ensemble, right? So suddenly something happened. Our log of omega b of E minus E nu is equal to log omega b of E minus beta E nu. Okay, let's call it equation number 3. So statistical mechanics, just like thermo, if you look at the nodes, it just looks like a bunch of algebra, but there is strong physical assumptions that are always being made. You know, if the bath was not much bigger than the system, then equilibrium would take much longer to happen, right? The bath cannot really tackle everything. Okay, so I'm going to write down equation 2 and equation 3 on the next page, and then we will combine them. So equation 2 was P nu proportional to exp of log of omega bath E minus E nu. That was equation number 2. And equation number 3 was that log of omega b of E minus E nu. And this is why you see why we kept the log. If we had not kept the log, the partial derivative would not have helped us, right? If at this stage I had absorbed the exponential and the log, the partial derivative of omega with respect to E is nothing, right? That has no thermodynamic significance. Is that clear? It's the partial derivative of the log of the microeconomical partition function with respect to energy, that is the inverse temperature. So the log had to stay inside the partial derivative or we would be screwed. So log omega b of E minus E nu is approximately log omega b E minus beta E nu. Okay, and that's equation 3. So let's put 3 in 2. And let's look at log of P nu. Okay, what is going to be log of P nu? Log of P nu is going to be log, like log of exponential of log. We're going total crazy. But that will help us stay with one of the logs. So we get rid of the outer exponential. That's what we're doing. So log of P nu is when this log and this exponential kill each other. And then we are left with log of P nu is equal to log of omega b of E minus E nu. And that is directly given in equation 3. So log of P nu is equal to log of omega b of E minus beta E nu. Therefore, P nu is equal to e to the power log of omega b of E multiplied by e to the power minus beta E nu, right? Does this thing depend on E nu? This is the number of microstates of the bath if it had a total energy E, right? If this is, so can E nu become negative? I'll have some issues. In our case, our E nu starts at 0, right? So this corresponds to, this is the number of microstates of the bath if E nu was equal to 0, right? That's the case. And E nu cannot go lower than that. And you have to be careful because energy is always true up to a reference, but this is the way we have defined it here. Like in our definition, it cannot really go lower than 0. So this thing does not depend on E nu, right? It is some prefactor. Therefore, we got our result of interest that P nu therefore is proportional to e to the power minus eta B nu. Let's give the proportionality constant a name. You might say it already has a name. It is e to the power log omega b of E, but that's a terrible name, right? So I will call it P nu is equal to 1 over Q e to the power minus beta E nu, where Q is a proportionality constant. However, Q is not just a proportionality constant, Q is the proportionality constant. It contains all information that you can care for possibly, and we'll just see in a moment. So this is our canonical ensemble probability of micro states. Okay, any questions about this?
Can you go over that? The thing you've written in red, just one more.
This one does not depend on E nu, and this one is number of microstates of the bath if E nu is equal to 0.
No, not the handwriting. Can you just explain that?
Which one?
I get that it's proportional. How did you just say it's the number of microstates?
It doesn't matter if that you don't like, then the thing to keep in mind is this one. This is the most important thing. Do you agree that it does not depend on E nu?
Yeah.
There is E nu, there is no E nu over here, right? So it's a proportionality constant, and we give this proportionality constant name 1 over Q. So Q depends on N because we have fixed the number of N. It depends on V, the total volume of the system, not the bath, just the system, and it depends on temperature, or accordingly beta, right? The inverse temperature. And this Q is known as canonical partition function. We are going to be spending a lot of time with this. Go ahead.
I have two questions. First one is the new probability or probability density?
I'll use probability loosely because that allows me to work with discrete states also. It's probability density.
And second, since nu is positive or zero, does it mean that the maximum probability is when nu is zero? And I don't understand physics of that.
Oh, it will become clear. We will talk about that. How does this? Because I also made the claim that all ensembles are the same in the large thermodynamic limit, right? So this looks very strange. This is telling us you're absolutely correct. Just hold on. That will become clear soon. Right?
This is probably I think sometimes
What's the difference between both?
my density is add up function. So it will integrate again.
Yeah. So the next slide will make it clear. Yeah.
You don't need to integrate again.
You don't need to integrate. I'm thinking about discrete states, so it's just a sum. So let me write down the key things. And the point that you made is, why is it maximum at E nu is equal to 0? Why is it saying that the system should not have any energy? Why does that make sense? It will become clear. Just a moment. So what have we said so far? We have, so just a brief recap. We have said in an NVT ensemble, the probability of a microstate nu of a system is 1 over Q e to the power minus beta E nu, where we want the probability should sum up to 1 over all microstates, right? In order to do that, what do we need? We need 1 over Q e to the power minus beta E nu is equal to 1, right? That's when it's going to happen. Q does not depend on nu, right? Q is, as we said, Q basically is this thing just re-expressed, and that does not depend on E nu. There is no dependence. So Q can go out. Therefore, 1 over Q summation nu e to the power minus beta E nu is equal to 1, or Q is equal to summation over all microstates e to the power minus beta E nu. So this is the value of the partition function. So we had equation number 4, T nu is equal to 1 by Q e to the power minus beta E nu. And this is equation number 5. Q is equal to summation over nu e to the power minus beta E nu. And you can make it density if you have continuous states. You just have to replace the summation with integral. So, and this Q is either a function of NVT, or it's the same as writing it as a function of NV beta. The meaning is understood. Some books write Q as Z, and that's why I keep using the indices, the variable that it depends on, because Z we are going to use for a system where even N can fluctuate. And the proof for that is identical to what we just did. Any questions about this? So let's plot this. So go ahead.
Can we go back to slides?
Couple slides. One more.
Yes. Yeah, like the very first line. Would it have still been like accurate if we just dropped the first omega, like omega system, even if it is small, without like taking the exponential of the log?
Are you saying that we could just remove this?
Like you said, Shannon does this, right? But
Yeah.
Is this
I think it's an approximation. I have gone back and forth over it. I think it's an approximation. I think you need to count it.
Yeah, because multiplication, like if it's small enough, then it can.
Yeah, but you're assuming small enough. So if E was
No,
not.
no. I mean, like if it is small enough, we cannot ignore it. It's multiplication, right?
But in the log, it's this term that you ignore it, right? Here you
Yes.
can.
Yeah, so my question is like, we cannot just ignore it on the level of like
No,
the very first.
no,
line.
no. Yeah. But Chandler does that. Now he's dead, so I cannot go and fight with him.
No,
I know. Huh?
You got empty.
No, 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 no.
Gonna be an article in Scientific American in the future.
What? Chandler was obnoxious. He would go to conferences and pick up fights with everyone.
Yeah, there's an article about it.
Him and Pablo de Benedetti, yes. That's
yeah,
his.
only one money this one.
Yeah. Okay. Let's look at P of E nu. How does it look? It looks like an exponential, right? So if you're plotting P of E nu versus E nu, it's telling us that the probability is going to be highest when E nu is equal to 0, and then it drops down, right? So this is in the canonical ensemble. In the microcanonical ensemble, we saw something different. Microcanonical ensemble said that this probability, if you plot P of E nu versus E nu, it's going to peak when E nu is equal to E, right? Microcanonical ensemble said that this is going to look like this. So there is sort of a contradiction. What's going on here? We'll come back to this in the next episode. Okay, it will take some, we will come back to it. I don't want to do it right now. I want to play a bit more with the partition function, and then I want to come back to this. But just remember that these two views actually reconcile, and the answer to this will come back from something I hinted last time. You have to multiply this with a Gaussian. Something goes down quickly, the number of state goes up very quickly. It's their product that looks like this. So, and that's important, and I want to spend time on it. So we will come back to this, and maybe later today or probably in next class. So, but let's go back to this partition function and play around with it. Okay. So once again, I will write it down because it's so important. P nu is equal to 1 over q e to the power minus beta e nu, where q is equal to summation over all microstates of e to the power minus eta b nu. So and also let's do a bit recap of both the ensembles we have studied. So we have our first ensemble that we studied, which was NVE, known as the microcanonical ensemble. In this ensemble, our partition function was denoted omega of NVE, and the connection to thermo was that S, the entropy, is equal to KB ln omega NVE. We did not prove this. Remember, we did not prove this, right? We just kind of threw it and said, look, it makes sense. Now we are going to prove everything else. Okay, that was one assumption that we made, which we showed that, oh, it kind of makes sense. It's good, you know. Now we have the canonical ensemble, NVT. In this one, the partition function is Q of NVT. The question is, what is the connection to thermo? Any ideas?
The Helmholtz free energy.
A is equal to what? Turns out it is equal to this. And this is not obvious. The log, so just like you had omega NVE, you take its log and you multiply it by KB, you get S. Here you take log of the canonical partition function and multiply it by a minus KB, you get A. And that's what we are going to do I do it? No. So we will prove this, okay? I can do it right away, but so there are two things I've hinted to. First of all, I will reconcile these viewpoints. Yeah, go ahead.
I was kind of confused. Are the units off between that? Shouldn't there be like a T in there?
Tell me.
Good question.
Good. Yeah, always do your dimensionality analysis. So we are going to get to this, and the idea would be to look at E minus TS. But the reason why it's kind of difficult to do this, because A is equal to E minus TS, right? Which E? Which S are you going to use? We just saw that in the canonical ensemble, E can take all of these values, right? So which E are we going to take here? We don't even know how is the entropy going to behave in the canonical ensemble, right? So it's a bit hard. We will have to think about the average value of the energy and the average value of the entropy in order to do this, right? Which brings us to the next point, which is average thermodynamical. And now I have kept murmuring by parts, but not really used it. Now we are getting heavy into by parts land. So I hope you have your by parts warmed up.
But over the thermodynamic limit, won't all these quantities quote unquote average?
Yeah, we will see all of that. Why the average does not really matter. Why you can just write down the thing. We'll look at averages today, and then Thursday we'll look at fluctuations, and we'll show how the fluctuations disappear. So we will look at average thermodynamic quantities from NVT ensemble. So the first quantity we want to look at is the average of the energy, right? Because it takes the value of along an exponential, right? And looks like the maximum, the probability is for energy is equal to 0, right? In this curve. But that does not mean the mean probability is 0, right? The mean probability is going to lie somewhere around here maybe, right? So let's calculate that mean probability. How do we calculate the mean of anything? Any ideas? Simpler. Huh? We need the average, right? So in order to, ergodicity is always there. That's a smart answer. If you are in you will ace your co-op. The professor asks a question and you answer, I don't know, ergodicity, and the professor is like, maybe he's just like BSing, or maybe he's really profound. And I don't know. No, you have the right idea, but let's make it simpler. So we want to calculate the average value of the energy, which we are going to denote through either of these symbols. And we know the energy can take different values in different microstates, right? It can take the value in u, in a microstate nu. And we multiply it by the probability of the microstate in u, which is ergodicity. So you're correct, I guess. So that's the probability. Now we have calculated the value of P nu, right? What was the value of P nu? That was 1 over Q summation nu e to the power minus beta nu multiplied by E nu. Right? This is the average of the energy. What can we do with this though? Those of you who have taken StatMat previously know what we are going to do next. Those who have not taken, the next couple of lines are going to look bizarrely confusing. It's like I'm pulling a rabbit out of a hat. So I'm going to go very, very slowly. I want to tell you the result before I go into the proof, okay? The result that we are going to show is that the average value of E, and so what do we want to do here? Why am I not happy with this result? Because it's like I still have microcanonical states dangling, right? Sorry, microstates dangling, right? New. For canonical ensemble, I showed how something could be obtained from omega just by taking its log, right? Sorry, for microcanonical ensemble. For the other quantities, I showed how you could get pressure, for example, by differentiating log of omega with respect to something else, right? So here I want to come up with a relation that does not want me to look at microstates separately, but if I know the partition function, I can manipulate it to get the quantity of interest, right? And what I'm going to show next is that E bar, the average value of the energy, is related to minus partial of log Q by partial of beta at constant N and V. And this is going to be equation number 6. This is what we would like to prove. And this is the proof. and looks very strange. If you didn't know this answer and just try to start from the equation over here, you will probably get stuck. It's one of those things, unless you have done StatMech a few times. So it's very important that today, when you go home, you become very familiar with this type of manipulation. How am I getting an average values out of partition function? And Thursday's class, how am I getting fluctuations or variances out of partition function? So how should I proceed? Well, let's do the math. Let's calculate minus partial ln q by partial beta at constant nv. What is that going to be? That is going to be minus 1 over q partial q by partial beta at constant n over v, right? Can we do something with this one? Let's look at Q. What was Q? Q was summation over microstates e to the power minus beta e nu, right? This was our canonical partition function. So let's differentiate this with respect to beta. Partial Q by partial beta. How much is that going to be? We go to every microstate, we differentiate it with respect to beta at constant n and v. So what we are going to get is a minus e nu multiplied by e to the power minus beta e nu. I'm going to pause for just a moment, and I want this operation to be extremely clear to everyone, because suddenly we have changed our notion of what's a variable here, right? So this q depends on beta, it depends on e nu, right? It depends on n also, but there is no n hanging over here, right? So we are differentiating it for a given microstate, for a given energy. So partial q by partial beta at constant nv becomes summing over all microstates minus e nu e to the power minus beta e nu. And now, actually, let's call this as equation number 6a, and let's call this as 6b. Okay. And let's call this as equation 7. Notice equation 6a, which we agree is the average value of the energy. It's kind of similar to 7, right? You're summing the same thing. You have e to the power minus beta e nu multiplied by e nu. That's what you have by partial q by partial beta also, right? So now if we look at 6a, what do we have? We have E bar is equal to 1 by q summation nu. We can write it as minus e nu. We just have to put a minus sign over here, right, up front, multiplied by e to the power minus beta e nu. This is 6a. And that's exactly the same as 7, apart from a 1 over q, right? So this term over here is exactly the same as this term. Therefore, E bar is equal to minus 1 over q partial q by partial beta at constant n and v. And that is just this thing, right? That is just minus partial of log q. So this is equal to minus partial log q by partial beta at constant nv. In other words, if you were able to calculate the value of the partition function, and if you differentiated its log with respect to beta, you would get the average energy of the system. Now, at this point, if you haven't done StatMech, which is many of you, it would feel, why would we ever care about something like this? When you get to your second homework, you will work on problems where you will calculate Q. It's actually easy to do that. And then you can get all sorts of properties out of it. So we just showed one connection to thermodynamics. And it's indirect. We haven't yet showed, we expect, due to our superior knowledge of Chem 684, that canonical partition function must be connected to the Helmholtz free energy, right? Why do we expect that? Because Helmholtz free energy also had natural variables NVT. So we expect there is going to be a relation, but we don't know quite yet. I just wrote it down. We haven't proven it. In order to prove it, I need average energy and I need average entropy. So I've just written down average energy and we will keep working our way through it. Any questions about this?
If you didn't know 6b,
What?
If you didn't know the final expression you're looking at.
Yeah.
How do you approach?
Memory.
I mean, even in like Stanford as an undergrad, they just you saw-
No, it's not clear, but you use your motivation that you want it to come out of something related to log Q, and you want it to be either value of log Q or first derivative of log Q, right? So it's not obvious. It's not obvious. That's why I said this proof is a bit harsh if you haven't seen it, and so I mean, it's a good exercise. Just go home today and remove everything except delete all of this. Don't worry, I will bring it back in the notes. I think delete all of this and just try to start from here and derive this expression or derive something, and you will get stuck just starting from this equation. Let's bring me. Did I get everything back? Yeah, I think so. Okay, good. So we have shown how average energy is related to partial of the log of the partition function with respect to beta. And what do I want to do next? Yeah, I need to talk about the variance of energy. The math becomes even gnarlier before I get to proving that it is connected to the Helmholtz free energy. Otherwise, I cannot really make a good argument for that. So we calculate the variance, we calculate the mean of an energy, right? Mean of the energy, because we know it's a probability density. Anytime you have a probability density, you can calculate average value of a random variable. But that's not the only thing you can do. You can also calculate fluctuations in that random variable, right? How much further is it going to be from the average energy? So what we want to do next is to calculate the variance in E. And this is not just a mathematical exercise to collectively suffer, but it actually allows us to get, it will allow us to prove both those things. How do the canonical and the macrocanonical connect to each other? And how do we show the connection to Helmholtz? In order to do that, we have to think about the variance in energy. So how do I define the variance in energy? The variance in energy, the variance in anything is given as the expectation value of E minus mean of E squared, right? This is the definition of variance. If you're rusty on this, I really recommend going and looking up Wikipedia on variance and standard deviation. They are going to show up again and again and again. And standard deviation is the square root of the variance, right? So we want to calculate this thing. Another way to denote this is average value of delta E square, right? Where we have defined delta E as how different is the energy from the average energy, right? So that's what we want to calculate. Okay, let's get started. So the variance of energy, again, let me tell you the result, which is super cool.
Like that's what you're saying?
Yeah.
Is it going to be related to the second derivative of?
It will be, but that makes that is intuitive to some people. It's possibly intuitive to JP, and it's nice. But I will show you something even nicer. It's actually related to. It will come through second derivative, but it is related to the heat capacity. That's very beautiful. That is our example, our first example of really work done by Onsager, who won the Nobel Prize on fluctuation dissipation theorem. Why is it so beautiful? Because you have a system where the energy is changing, right? It's fluctuating. And if you measure how much variance it has, you can talk about how much heat will you have to pump into the system in order to change its temperature by 1 Kelvin. These are two completely different things, right? In order to increase the temperature of this coffee, I have to put a burner over here and heat it and then measure how much heat did I have to give. Now I say, forget about the burner or anything. Let the coffee sit at this fixed temperature and just observe the coffee molecules and measure how much is their energy changing. And if you could measure the variance of this energy, you again get the heat capacity. So this is super beautiful. This is showing heat capacity is connected to microscopic fluctuations. And this shows up in many, many different domains of physics. Chandler has a chapter on this. You can go and read it up later. We are not going to cover that really in this course, but you can read. Yeah, go ahead, Patrick.
Is the dissipation part, so CV is related to this?
Yeah, that's the idea. The CV is the dissipative part. So this is connecting to that, right? This is fluctuation, and CV is how, what you do with the heat, right? You pump some heat into it, and what happens to it? That's why we call it dissipation.
Just dissipates through like
Exactly. In all degrees of freedom, right? Why do we call it dissipated? Because anytime I heat this, the heat is lost, right? It's equilibrated over all the degrees of freedom. So this is a beautiful relation. In fact, I will keep saying it's super beautiful. I like it a lot. But let's try to prove this. In order to prove this, we have to work through a bit of math. Okay. So the proof is, let's look at the variance of E. And the variance of E is going to be average value of E minus E bar squared, right? And what is that? That is going to be average value of, let's sum it up, E square plus, and you have to be careful here, square of the average minus 2 minus E bar minus E bar E. We are not doing quantum mechanics. So E bar is the same as E bar E. Furthermore, E bar is just a number, right? It's a scalar, so there is no problem, right? It commutes for sure. So this is going to be E square plus E bar. But when you do quantum mechanics, there is a reason why I wrote it down this way. If you're doing things like this in quantum statistical mechanics, you have to be very, very careful. If it's a scalar, no problem. But if both things are observables, then of course it's problematic. This is going to be minus 2E E bar. And now we have to calculate the average. Okay, let's go one step further. Average of a sum is sum of average, right? Even in quantum mechanics, there is no problem with that, right? So this is going to be average of E square plus average of E bar square minus 2 multiplied by average of E bar. What can we do now? This one we are going to keep as average of E square. This one we are going to keep as, I'll just write this down as average. I will write it down. I won't use the bracket inside. What can we do with the right thing? E bar can come outside because E bar is a number, right? It's some value. This E bar over here is just a number, some average energy. Taking average of a number does not make sense, right? You take average of an observable, average of a number, it's a fixed number. So what we can do is to bring it outside and write it as minus 2 E bar multiplied by average of E. What is that? That is E square plus E square minus 2 E bar. Did I miss something? Are you sure?
Is the E bar a number as well?
The expectation of the E bar squared is E bar.
Yeah, E bar squared is just a number.
Yeah, but it's not going to take me where I want to go. So I'm sad.
It's expectations of square minus square expectation.
I want one term to disappear.
Yeah, you're gonna get, if it's 1 minus 2 is 1.
Yeah, that's right.
It's minus
Yeah.
one.
You get what the variance should be.
Why? So this is E square. This is,
E bar squared.
It's E bar squared is just.
oh yeah,
It's a number.
It's just a number.
oh yeah. Oh yeah, now I'm happy. Everyone happy? Good. Because this average also does not make sense, right? Because you have already taken a number, a number inside. So what is this? Yeah, I just wrote down the formula for variance. This has nothing to do with StatMech. This is true for all variances. So this is going to be average of E square minus square of average, right? That's the variance. And this is well known for a variance, so you don't have to derive this, but it's good to go through it again because I always find this operation confusing. Okay, so let's go to the next page and I will write down the final result. We have variance of E, not the result, but the thing that we are using, which is equal to average of delta E square is equal to average of E square minus square of average. Now we can use our superior knowledge of statistical mechanics that we have already built. We have calculated the value of a microstate. So we can write both of these in terms of sum. We can say the first one is going to be summing over all microstates P nu multiplied by the square of the energy of that microstate, right? That's exactly what it is. So pay attention to this. This is what we have. Average value of E square is average over microstates P nu multiplied by E nu square. While this one is minus P nu E nu whole squared, right? That's what we have. I will get to this first term in a moment. Let's write down the second one. The second one we just calculated. We showed the average value of the energy. Let's call it equation number 8. Equation number 8 says that average value of the energy is minus log Q, minus partial log Q by partial beta, right?
Already equation 16.
Is it?
Yeah.
It's so important. We give it 2 names. So that's going to be square of 1 over Q partial Q by partial beta at constant NV, right? Partial log Q is the same as 1 over Q partial Q. The first one we have to deal with. Again, you get stuck. It's not clear how to do it. You have to go and do a very similar manipulation that you did in order to get P nu, E nu, in order to get the first one. I'll write down the result and then I'll show you how we get it. Okay, so this one turns out to be 1 over Q double derivative of Q with respect to beta square at constant NV. Okay. So I guess we haven't used by parts today, but we have used the other operation, which is differentiating the partition function, just differentiate it a ton of times. Okay, so let's try to prove this relation. That how do we get this? And you'd start to develop intuition for this. Anytime you see squares of observables, it's related to double derivative of the partition function. Anytime you see mean of observable, it's related to single derivative. So in your next homework, guess what is coming? Average value of the 4th power of an observable. You will be taking 4th derivatives and having a lot of fun. That connects to, actually it has thermodynamic repercussions. There is a book by Patria on statistical mechanics. Its homework problems are all full of like 3rd derivative and 4th derivative and 5th derivative. But you can see that those things are connected to compressibility and things like that. There are huge connections with these 3rd derivatives. So next homework, be ready to do a lot of differentiation of Q. First, you will calculate Q. Next homework, it will be all about, do I calculate Q or do I calculate omega? You have to make an informed choice. Now that you have calculated it, do I differentiate it once? Do I differentiate twice? Do I differentiate it thrice? You have to keep thinking about it. Okay, that's that type of stuff. So let's prove this one. We will start again in the opposite manner. I know it's terrible, but that's what it is. So we have Q is equal to summation nu e to the power minus beta e nu. So let's differentiate it once. And I will omit the what is being held constant in the differentiation derivative just to be lazy. Partial Q by partial beta is equal to minus summation over nu e to the power minus beta e nu. Let's differentiate it once again. Partial square Q by partial beta square is going to be one more derivative. The minus becomes a plus nu e nu square e to the power minus beta e nu. Now you see how it looks just like the average value of the probability. sorry, average value of E nu square, right? Because what is this? This is, if I multiply and divide by Q, Q multiplied by 1 over Q, and do this, it is E nu square e to the power minus beta E nu. And what is that? That is Q multiplied by summation nu E nu square P nu, right? And what is this? This is the average value of E nu square, right? So 1 over Q summation square double derivative of Q with respect to beta is equal to this thing. And that's what we were proving there, right? So we had gone up to equation number 8, which was a fake equation because it was copycat of 6p, but that's okay. We will show that equation a lot of respect.
Can you just explain that last step, the multiplying and dividing by Q?
Well, I just multiply, divide.
No.
It's a chat GPT answer. Yeah, go ahead.
No. Okay, fine.
It is really
Yeah,
trivial.
I
It was
got
not
it.
wrong.
Yeah.
It's trivial when you see it. But if I close the notes and ask you to do it today, you will get confused. I will get confused because it's not obvious. You know, you have to. If you didn't know the answer and I asked you to, if I removed this and asked you to write down what it would be, it's not easy. You have to remember that second moments of observables are related to second derivatives of partition function. That's the message here. Okay, so let's call this as equation number 9, and we will come back to equation number 9 on next page to prove our beautiful heat capacity relation. And then I'll stop. Yeah, go ahead, Sophia.
I'm still kind of confused where the Q goes.
Oh, let me be slower. Yeah, I used to hate it when people would just like erase things and then be like, oh, it disappeared. Okay, let's stay with me, Sophia. Okay, so this thing is going to be nu E nu square. I can bring the Q inside, right? You happy with this? I just brought the Q inside because it does not depend on microstates. This has a name. This is P nu. P nu is e to the power minus beta E nu divided by Q, right? That is the probability of a microstate. So this is Q summation nu E nu square P nu, right? Now I take this Q to the right hand side and I say 1 by Q partial square Q by partial beta square is equal to summation nu E nu square P nu. That's all I did. Okay, and that's what's written over here. So let's look at equation 9. I will write it on the next page. So equation 9 says that variance of energy is equal to 1 over Q double derivative of Q with respect to beta at constant NV minus 1 over Q square partial Q by partial beta whole square at constant NV. And that's equation number 9. What can we do now? We're kind of stuck. I'm going to use one more magic algebra trick because it is magic. If you don't know it, I mean, I don't know what to say, but you develop intuition and then it becomes clear. This thing, which is a difference of a double derivative and the square of a partial derivative, can be simplified. This thing is equal to partial log of Q by partial beta square at constant NV. And I'm not going to do the proof of this. This is DIY at home. I will put it probably in the next homework. So you work through it. It's really simple. Again, it's one of those things, start from the equation 10, then you will see equation 9 follows immediately. There is no problem. Because it's a log, you use product rule and you get it done, okay? But you have to take my word, it's 2 lines of algebra. Now that we have this, we can go one step further. We can actually do some physics with it. We can say that therefore variance E is equal to partial by partial beta of partial ln Q by partial beta at constant NV, right? This is also constant NV. The term in here, has this showed up before? How, when, where? It's the average energy. We just derived that, right? So suddenly we have something interesting going on. This is partial by partial beta of average energy with a minus sign at constant NV, right? That's very nice. I like it a lot because now we can do one more thing. We can say that variance of E is therefore equal to minus partial of average of energy with partial T multiplied by partial T by partial beta at constant NV. Oh, something happened. The first one, that should remind you of 684. Does it? Why?
I mean, it's
How? Tell me how. What exactly?
just CV.
Why is it CV? So let's write down the proof. Remember we did this, that du is partial u by partial t at constant v multiplied by dv plus partial u by partial v at constant t by, sorry, dt plus this thing, right? If it's at constant volume, this goes to 0 at constant volume. There is a third term also which goes to 0 at constant number. Point being that minus partial E by partial T at constant NV, if you are ready to draw parallel with thermodynamics, and if you're willing to say that this is the same as partial U by partial T at constant N and V, where U is the thermodynamic energy. Thermodynamics, we don't talk about averages. We don't talk about variances, right? Everything is observable. Then this is minus CV, right? Let's call this equation 11. So equation 11 just showed us that variance of E is equal to minus CV multiplied by this term. And that's actually quite easy. Partial T by partial beta is equal to partial T by partial 1 over kBT, right? So that's a simple derivative. You can do that. You do it the other way and then write it back, right? It's 1 over the simple derivative. So what do you get from this? You get that this is minus CV multiplied by minus kBT square. So this thing comes out to be minus kBT square. And we have our beautiful relation that the variance in energy is related to kBT square CV. That's where I'm going to stop today. It's a bunch of algebra. Please go through it once. I deliberately left one of the algebra things for you to do. So when you try it, some other things will become confusing to you and you will try to clean it up, but please try to go through this derivation once. And next time we are going to show that this variance in energy actually starts to become less and less important as we start to achieve the thermodynamic limit. And that will solve our conundrum of reconciling both of these pictures, you know, the energy, how does it behave? And then we will look at how does the Helmholtz energy come out of this. That's what we are going to do next time. And then I will look at a practical problem using microcanonical and canonical and show you the results are the same. It sounds like a lot, but this was the heavier part. Next time will become easy if you please put some work through what we did today.